your stage.
Yeah, okay. Yeah, thank you, Kai Cao. And good afternoon. My name is Ke, and I'm a software engineer from Intel Data Center and AI software group, and working mainly on like AI framework, ecosystem integration, and optimization, topics like Hugging Face, TGI, TEI, and of course, including this vLLM, right? So this special session. So earlier, you guys heard about like vLLM deployment at Uber and at Apple, right? So for their GenAI applications. Now let's switch the topic. Let's look at how to best support vLLM on Intel platforms. So today I'll cover Intel Xeon CPU platform as well as data center GPU platform. So Intel also has AI accelerator platform called Gaudi. Like you probably heard about that, right? But due to the limited time, so I don't plan to cover in this session. But we have a demo booth in the demo area. Our team is showing like how to deploy GenAI end-to-end applications using vLLM on Gaudi platforms. Achida, so she's my colleague, and so she's there and can answer any questions related to product. So if you have any technical questions, I'm here also can discuss offline, right? So if you have interest in that particular Gaudi topics. Now back to the session. So this work is mainly done by my team in China and the US, and Yuan Zhou, so who is the co-author for this talk. He is based in Shanghai, but he is not here. Actually, this week is China's national holiday. The quick agenda. So I'll first talk about Intel CPU and the GPU introduction, its AI-related feature, and then talk about the software stacks on Intel CPU and GPU. In second part, I'll talk about vLLM integration on Intel CPU and GPU platforms, and the key features, enabling status, and the next step on Intel platforms. So last part, I'll also present some performance numbers from our latest platforms. Okay. Xeon, so right. So I would say Xeon is one of the most widely deployed AI computer platform in the world, right? So supporting diverse applications like database, like web service, HPC, high performance computing, and of course including AI workload, right? And so starting from 4th generation Xeon, so previously codenamed Sapphire Rapid, Intel added AMX into every physical core of Xeon. So AMX stands for Advanced Matrix Extension. So this is in addition to the AVX 512, so which was added a few years back. So AMX is mainly for the matrix acceleration, and and AVX is mainly for the vector acceleration, right? So those both of them are very important to accelerate AI workload. So last month, actually to be accurate, it's 2 weeks ago, Intel launched the Xeon 6, which is the latest generation of Xeon. So with Xeon 6, it can deliver, like the numbers shows on the right side. So 1.9x performance per watt kind of improvement, gen over gen, so which is efficiency improvement. And then from HPC workload, it can deliver up to 2.5x, so gen over gen. And it also delivers 5.5x speed up for the AI inference workload comparing to our competitors. Xeon 6 is already available on Intel's developer cloud, and we are working with our partners to make it available to all of our customers and partners and users. So this is the latest generation, right? So the previous generation is the 5th gen, so codename EMR, more rapid. like our partners like Ali, Baba, so they showed a blog, I believe it's earlier this year, so January, February timeframe, and showed the TCO reduction by 50%. The figure I showed on the bottom right, so it is in Chinese, but basically it says to deploy medium to small size of language model. So the TCO reduction is by 50%. So EMI is right now is widely available at CSPs like GCP as well as Ali Cloud, right? So there are many other cloud providers that are also deploying EMR in larger scale. Xeon is good in support those smaller models, but we all know in order to support those bigger ones, it is best with GPU and accelerators. So Intel has a GPU IP called XeIP, so it supports across multiple segments, including like a PC and including like edge and also data center, right? And from data center side, we have the GPU Max, which got largely deployed at Argonne National Lab and to train their trillion parameter models. So there's a consortium called the TPC, trillion parameter model, and Intel and like Argonne and other partners, right? So they are working together to train the model and to address like those challenging research problems, right? GPU Max is mainly for training and inference purpose, and we also have Flex series of GPU purposely built for inference workload in the data center side. And we also have Arc GPU, so they are like one is with discrete GPU and the other is with integrated GPU for our client laptop and desktop product. Earlier I talked about Gaudi. Gaudi 2 was announced last year and right now in production and large deployment in our customer side. So Gaudi 2 is with TSMC 7 nanometer. And together with GenAI launch, right, and also Gaudi 3 was also launched 2 weeks ago. And the Gaudi 3 is with TSMC 3 nanometers. And so with Gaudi 3, it can deliver like 20% more AI throughput and compared to H100, right? And also it can deliver like a 2x in terms of performance per watt, right? So from TCO perspective. So which makes it a viable alternative to the H100. Gaudi 3 and Gaudi 2 both are also available in Intel's developer cloud. And we are working with partners like IBM Cloud and Denver Data Works, right, to make it available to more customers and more developers. We know like availability is a problem, right? That's why we co-work with those partners as soon as we can. Last but not least is Falcon Shell. So this is our next generation general purpose GPU platform, combining both our Gaudi product line as well as the current GPU product line, right? So which will be very important product in our roadmap. Okay, so when talking about GPU, people talk about CUDA, right? And then on Intel platform, we have SQL. So SQL is a royalty-free open standard developed by the Kronos Group. Allows developer to program heterogeneous architecture using standard C++ and also with some extensions. And DPC++, which means Data Parallel C++, is Intel's implementation for the SQL. It works like on multiple different devices, right? Like a CPU, GPU, and also FPGA platform. So there are many similarities between like a CUDA and a SQL because essentially they are just like programming languages for the parallel computing. purpose, right? And but also there are some differences I list here, like SIMD versus SIMT, and the working group versus thread group, and so on, right? I don't plan to talk in more details because it deserves another big topic. Instead, I just want to show a quick example code, right? So this is the Silu and the Mao kernel, so that we developed and also integrated into the vLLM optimization on our PVC platform. So you can see it is very similar like CUDA code, right? On the top right, it's the kernel itself written in a C++ template code. And then in the bottom part, it shows like how it is parallelized in the loop optimization and also like how it is code, right? So in summary, you have CUDA and also Catalyst, right? Catalyst is a template library, but equivalently on Intel platform, you have SQL and then XETLA, right? XETLA is the template library for our GPU platform. Okay, so I talked about our CPU, GPU platform and its AI-related features, and now let's talk about how are they integrated into the PyTorch ecosystem. Intel is among the top 3 contributors for the PyTorch community. So the PyTorch conference, right, so happened a few weeks ago, highlighted this one, so like Intel's contribution into areas like CPU backend and also Torch compile. And so one of the highlights was Intel's GPU, so finally got merged into PyTorch and becomes in-tree support. And then Intel extension for PyTorch, also known as IPEX, it is for that staging purpose, upstream purpose, and it also provides up-to-date features that optimize like for an extra performance boot on Intel's CPU and XPU platforms. And we added kernels like attention kernels and low precision kernels, right? Lots of things are added into IPEX and integrate into the vLLM project, right? So the right side, it's a high-level block diagram. It's a high-level block diagram. So from bottom up, so we have OpenMP thread runtime, that is for the CPU backend. And then on the GPU side, we have the SQL runtime for the GPU backend. And on top of that, we have libraries like 1DN, 1MKL. So MKL stands for the mass kernel library. So they provide functions like a gem, like a convolution, like FFT, and so on. So these kernels are further integrated into the PyTorch, and then on top of that, we provide A10 OPs for the eager mode, and then graph OPs for the graph mode. So like the typical optimizations we usually do is, for example, some of the kernel fusion, and some of, for example, low precision, and also like memory layout optimization, and so on, right? So those optimizations put into the IPEX library. Okay, so now I'll cover the second part, vLLM integration. So our goal is very simple. We want to provide a native developer experience and user experience when you run vLLM on Intel platform, right? So which means you can build the Docker container for Intel's CPU, GPU, and also HPU platform, right? And then as a user, you just run your code out of box. You don't have to change any of your user code, right? So what I put here is the zero code change. Then IPEX as the unified backend engine here, so for both CPU and the XPU to minimize the integration effort and deliver the consistent APIs. So in order to achieve my team co-worked with the vLLM team very closely and implemented this multi-backend kind of integration for different hardwares, right, but at OP layer. So through this way, so we can maximize the reuse of the core vLLM features, right? We don't like reinvent the wheel, right? And we only have to implement those kernels for those particular hardware platforms. So following this design, so for CPU and the XPU backend, so we have this IPEX integration. And then on the Gaudi platform, we followed the same design and doing those OP level integration, right? And now, so it is, the PR is under review, and right now it's in the fork, but the PR is under review, and I discussed it with Wu Suk yesterday, so it will be soon into the vLLM mainline as well. So to recap, so the CPU is mainly with the AMX acceleration, right? Develop kernels around that, and then the GPU is mainly around the XMX, right? So kernels around that. So a little bit of history. So my team started working on the vLLM support on Intel platform starting from like a Q4 last year. Start with the CPU support, and later on we added GPU support. And at this moment, both CPU and the GPU, they are in the vLLM mainline, right? And we are working with the vLLM team to add more features into that, right? So like quantization will be a big topic. I will talk about quantization later in the later slides. So I already talked about multi-backend like a device abstraction design, right? And so this allows us to add more hardware support easily. Right? I just skip this page. So continuous batching and page attention. So this was the original shining point when vLLM was introduced more than a year ago, right? But that was started with the GPU optimization in mind. But I would argue this is also very important for CPU platforms as well. Even though on CPU platform you have much larger DDR size, DDR capacity, right? But you need to deal with, for example, variable input length and output length, right? So the memory allocation cannot be used fixed one. You need to have a smart design. And since this is for serving scenarios, so meaning you need to run this service for a long time, and then you need to have a mechanism to avoid memory fragmentation and out of memory things, right? Even on CPU, right? We have JE-malloc and TC-malloc on CPU, but that is not enough. We need a better way. So with continuous batching and page attention, so KV cache memory management becomes much easier, and also it is very beneficial for adding advanced features like tearing or remote KV cache pulls, right? Those features. And then all this attention and those stuff, right? And from kernel perspective, as I said earlier, so they are all implemented in the IPEX library. Talk about CPU backend, right? So it is different from the GPU backend. And then on CPU, we need to specifically deal with situations like a NUMA, a synchronized execution. And there are some common practices, right? So some optimization I listed below. So if you want to reduce the latency for latency constrained deployment, especially for large models, and then you need to do a tensor parallelization. And but in general, if you want to maximize the throughput, and you do data parallelization kind of way, right? And then there's a HTTP serving component and to be decoupled from inference components. This was one of the recent features, right? And we also need to do it properly for the CPU. And on the right side, I put a very simple, simple but typical CPU setups, right? So you have NGIX as a load balancer. You receive many user requests from the client asynchronously, and then you dispatch it to the different vLLM instances in the right side, right? So assume one socket, you have two NUMA, and then for a dual socket system, you end up with 4 vLLM instances running at the same time to get the maximum throughput. And so this is like a tensor parallelization, right? And so following vLLM design, so on the CPU backend, as I said, right, tensor parallelization can benefit for those latency constrained kind of deployment. we need to deal with the NUMA thing, right? So conceptual-wise, you can consider like one NUMA domain is conceptualized like a one GPU card, right? And then you need to handle those model sharding properly. You do the model sharding on multi-GPU kind of setup. You do the similar thing on the like multi-NUMA setup on the CPU kind of system, right? Each NUMA node so like acting as a worker, and then there's local shared memory-based communication OPs, so to improve the efficiency. Since we are using OP-level integration, so the integration to support this actually is pretty straightforward. We just need to implement those special OPs, right? And then the diagram, so there's, from KV cache perspective, so there's GPU block allocator, and then we also need to have the CPU block allocator. Then in each of the workers, right, we put those page retention and some of the linear layer optimization, like some of the communication OPs, right? And so that is the same for each of the workers. Now the quantization topic, right? I mentioned earlier, and actually Brian from NeuroMagic, they did a very good job yesterday talking about quantization, the basics, right? So why quantization is important, how it can improve those throughput, right? And because there are two things. One is you can greatly reduce the memory traffic, right? Second part is you can leverage low precision acceleration for either tensor core in GPU case or AMX, XMX on the Intel platforms. Right, and so quantization in high level, there are two parts. So one is how to generate a quantization recipe using algorithms like weight only quantization or weight and activation quantization, smooth quanta, whatever other method, right? So quantize a model from full precision to low precision, right? Second, of course, with accuracy, target, meet the target. Second part is now with the quantized model, how can you run inference efficiently, right, using a serving framework, right? And so the first part actually has nothing to do with serving. It's mainly the second part. Robert mentioned many quantization algorithms yesterday. So some of them are already supported on CPU side as well. And this is one of the features we plan to do in Q4 this year, right? But the current status is weight 8, A8, so it is already working. I'll talk about those numbers in a minute. And then auto AWQ, so PR under review, and auto GPTQ, it is also almost ready. And so from right side, so you can see roughly it's like a 30% improvement, right? WA A8 versus BF16. This is just a starting point, because at this moment we just did the simple descaler from int8 to the BF16. Then the KV cache and also the computation still happens in those 16-bit precision, right? And so you can see the opportunities we can have to reduce the computation, as well as also to make the KV cache fully in int8 format. Those works are ongoing. Okay, so last part, I want to mention some performance numbers. So the first one is about AMX versus AVX 512, right? I mentioned earlier, so in theory, from hardware perspective, there's 16x speed up. Then we measured it on a Ice Lake versus EMR, and then the measure number is 15.11 speed up, right? And so which means it's best to use the latest Xeon platform in order to get best performance as well as performance per dollar. Now, second is latency. So we benchmarked several common models on the 5th gen Xeon with IPEX. So here the left side figure is the second token latency, and the right side figure is the first token latency. And then the blue bar is with one socket result with TP equals to 1, and then black bar is two socket with TP equals to 2. And then from the first token latency perspective, roughly in the one sock case is roughly 1 second, right, for the first token latency. And then if you use two sock with TP equals to 2, it's about 0.5 second, right? So meaning it scales linearly, right? Because it's in the first token latency case, it's mainly computation bounded. So this aligns with this result. Then for the second token latency, there's improvement by using like a two socket, but that is the improvement is not as much as the first token case, because for the second token, right, it is not computation bounded anymore. It's mainly the memory bounded, right? But nevertheless, so meaning you run those models, right? So like a 6, 7, 8 billion model on Xeon platform, you get decent performance, right? So making those Xeon a viable platform to run those like smaller models. So last one, so I want to also quickly show some initial performance numbers we measured on the Granite Rapid, so the latest generation of Xeon. So we picked the Llama 3 8 billion model, and then we compared against the 5th generation and the 6th generation. So like the throughput, right? So using vLLM, like offline throughput benchmark script using shared GPT dataset. So you can see it's roughly like a 2x throughput performance improvement, right? So it's mainly because of memory bandwidth improvement as well as the number of cores improvement, right, in this case. But the number actually is pretty good, and from the offline throughput number, so it is already very competitive even with some high-end NVIDIA GPUs. Okay, I think that's the last page, and to quickly recap, so I want to say two things. One is Intel's CPU and GPU platform, like the performance is decent for those GenAI models, GenAI applications, right? First. Second is Intel CPU and GPU, they are fully supported in vLLM mainline, and there are more features. We are working with VM teams, and we'll bring like more performance, more features there. Okay, now I think we're open for questions.
Okay, thank you. Yeah, if you have any like questions, we can hand you the microphone.
So with respect to where are you fundamentally finding the usages as, in the CPUs as compared to, in accelerators?
Yeah, so that is a very good question. So CPU, right, so it's designed for general purpose. As I said earlier, right, Xeon can support very diverse set of different workload, right? So database, blah, blah, lots of things, right? So then in terms of GenAI models, I would say, so it is it can support those smaller models pretty well, right? So less than 7 billion, and especially those embedding models, right? So pretty well, and on the other side, the CPU is like availability is very good, right? Not like a GPU, you cannot get this, get that, right? And then on CPU platform, for those smaller models, you can run many instances in parallel, right? And so like a small model plus big models, right, running on the GPU and accelerator side, I would say it's a good combination for the investment from enterprise perspective.
Cool. We can have one more question.
On the last slide just before this, yeah, these numbers that you have for tokens per second, is that for batch requests?
Yeah, batch. Otherwise, it cannot reach that high.
Yeah, okay, but what was the batch size for this?
Batch size, I believe it is 32 or 64. I need to check, but it's a batched inference.
And how many CPUs? Sorry.
CPU here is, so the left side EMR is with 64 core per socket and dual socket system. And on the GNR case is 96 core per socket and also dual socket. And they are not the top bin, like the top bin, for example, the GNR, it is up to, I think, 128 cores per socket.
Okay, thanks for the speaker again.
Okay, thank you.